Okay, so with this activity, we are going to be exploring some different polymers. Specifically, we're going to look at the big six polymers that are recyclable plastics, or at least they claim to be recyclable, and then we'll kind of compare them to some other polymers. So you should have a data sheet that asks you to collect some different information on them. And so I have some different samples here. So we want to look at, is it clear, transparent, like this is, or is it opaque like this is? Now, some plastics, actually most plastics can be made either way, but we kind of want to see, what the specific one we're looking at is. And then we're also going to look at some properties. Tensile strength would be, can I pull on it without it breaking? And then our elasticity would be, can I stretch it out and have it come back to the same state, same size and shape? And then flexibility is, can I change its shape fairly readily? So we'll start with some of the different numbers. I'm going to move some of these things out of the way for the moment. So I have the lid for a container here, and this is obviously clear. If I pull on it, it doesn't stretch out at all, but it also doesn't break. And I can bend it a little bit, but if I tried to bend it too much, if I tried to fold it in half, that's when I would start having it have little white marks or start to break a little bit. So it's a little bit flexible. So this is a number one, and it's got a label PETE. Now this sample here um, is black, so you can see it can also be made opaque as well. Um, so can't really stretch it out. I can bend it a little bit, and it does hold up if I try to stretch it. All right, so number two is often used for bags. Sometimes it's used for lids for like soda bottles and things, and that is high density polyethylene. So I've got a piece of bag here, and you can see it's fairly clear. You might be familiar with some of these, like Walmart's are usually gray, Kroger is usually tan, and it's perfectly clear, it's mostly clear. Now, what happens if I try to stretch it? So if I pull on it, I get what's called necking, meaning that it gets narrower in this range. And you can see when I let go, it didn't go back. It's not elastic. Um, it's not as strong when I stretch it. So it has lower tensile strength. All right. Now I'm going to skip to number four. We don't have examples of number three because the best example of that is PVC pipe, and I don't really have um, cut up pieces of that. So here we have number four. This is also often used for bags, and this is low density polyethylene. So they're very similar. This one tends to be more made of branched chains. And again, it's pretty flexible. It's pretty transparent. You can see through it. It's not as hazy as the number two was. And if I tug on it, again, I observe that necking. So it gets thinner there, doesn't return to its shape. It's not elastic and it has low tensile strength. Now, if I have a bottle cap, I would see that that would be a little bit different because it would probably have more tensile strength and we would observe less necking. So it really kind of depends on what form it's in. So for number five, I have this lid to a creamer container, and you can see that that is, and move this into the light here a little bit. This lid is opaque, and so it is not transparent. But then I have this, which was filmed from a bag, and that is more transparent. So it can be made either way. This one's pretty flexible, and this one, like most caps, isn't going to change shape a whole lot. You can see I can squeeze it a little here, but what is significant is right here at this seam, I can open and close this many times. Let me do it under here. Open and close this many times without having that break. Okay, so we need a polymer that has that property that it's not going to crack when I try to bend it. So it has some flexibility that allows us to do that. All right, so if I try to stretch out this one isn't as stretchy. Okay, so it's got more tensile strength than the number 4 and the number 2. And then our last one that we're going to do is number 6, polystyrene. So this can come in several forms. Sometimes it's called styrofoam if it's in this form. That's actually a brand name. So this is really just a polystyrene peanut that might be used for packing. We're moving away from using this kind. And then a lot of times it's used in cups and plates that are disposable, so like a solo cup. And so you can see this is um, in that variety. All right. And so kind of like with the number 5, it's a little bit flexible, but it's got some pretty good tensile strength. It's not going to stretch out. On the other hand, if I take this foam and I try to stretch it out, that's actually holding up pretty well. I was thinking it might separate, so depending on the direction that you're doing it. All right, so the form that it takes, whether I've blown a lot of gas into it, a lot of air into it, like with the foam, makes it less strong, weaker, and then for the plastic cups, it makes it a little bit stronger. Okay, so now we're going to look at the abrasion of these. And so I have on here 1, 2, 3, 4, and I'm sorry. I have on here 1, 2, 4, 5, and 6. And basically, I'm just going to see if I can scratch it with my fingernail. So number 1, I'm making a very faint mark on there, but basically not. Number 2, this I can scratch up with my fingernail. Number 4, I can scratch that up a little bit. Now, it might be interesting to test these with bottle caps because these are very thin. So this bottle cap doesn't say what it is, but it's probably either a 2 or a 5. And much like this clear plastic, you can tell that I've scratched it, but I'm not really making much of a mark on there. All right, for number 5, I'm not really getting any mark at all on here, so that's pretty abrasion resistant. And number 6, pretty abrasion resistant. Okay, so the next thing I want to look at is the density for each of these. And what we're going to do is we are going to compare the density to some liquids. And so we have here deionized water. We have a mixture of water and ethanol. And actually, let me do it that way. No, that's backwards. That's upside down. Well, we'll do it that way. It's going to be upside down. And then we just have pure ethanol. So if we look at the densities here, the density of water is about 1.0 gram per centimeter. Oops, that did not work. Put that there. The density of this mixture is about 0.94 grams per centimeter. Ooh, I should write that so we can read it. Okay, so 1.0, 0.94, so just a little bit less. And then for this one, closer to about 0.9. Okay, so we're not going to be able to come up with an exact number for our density, but we're going to be able to tell what it's in between. So what we're going to do is we're going to take a sample of each of these and drop them in each of the liquids. If it floats in the liquid, that tells us it is less dense than that. And if it sinks, it is more dense. So I'm going to start with number 1. And so this black piece will probably be easier to see. So I'm going to use that. Remember, that was number 1. And what we want to be careful of is that water has a pretty high surface tension. So if I just lay it on top, it might float anyway. So what I'll have to do is push the plastic under and see what happens. And we can see that that sinks. So that tells us that the polyethylene terephthalate, number one, is more dense than water. It has a density greater than one. So we don't need to test the others because if it's greater than one, it's greater than the others. All right, for number two, we're going to test this little piece of plastic bag. And again, we're going to push it under and see if it comes back up. Make sure all the air bubbles are out. We've got an air bubble there. All right, and give it a second to see what it's going to do. And it is coming back up to the surface. It is not sinking. So that tells us it is less dense than water. Now, before I test it in the next liquid, I don't want to mix the more water in, so I'm just going to dry it off a little bit. And then we're going to try it in the mixture. So again, just letting it float on the surface doesn't really tell us anything. We've got to get the air bubbles out from underneath, push it under, and see if it sinks. And so it's kind of hovering for the moment. We'll see what happens. Got a little air bubble there. So since this isn't going down and it's not really rising back up, this tells us its density is pretty close to that 0.94. Okay. So next we are going to, again, we're skipping number 3. Next, we're going to try number 4. So remember, the number 2 was the high density polyethylene. The number 4 is the low density. So we should expect this one to float on the mixture. But let's test it on the water, just so we're doing the same for everything. Push it under. Make sure we got no air bubbles attached to it. And give it a second. And here it comes right back up to the surface. See if it's floating there. All right, so we're going to dry this one off. And then we're going to put it on the mixture. Put it underneath, make sure there's no air bubbles. Give it a second. Now it's not popping right back up the way it did before, but it is coming back up a little bit. So this is less dense than the mixture. Let's see how it compares to the ethanol. Put it in here. It sinks to the bottom of the ethanol pretty quickly. So it's down there, the bottom. And so that tells us it is somewhere between 0.9 and 0.94. All right, let's try number 5. So we have number 5 here. I'm going to try it on the water. See if we can get it to go under. And it's just coming right back to the surface. It doesn't want to sink at all. So we're going to say that is definitely less dense than the water. Now we're going to try it in the mixture. Stick it under there. And again, it's coming right back to the surface. You probably can't see it in there, but it is popped up to the surface here. So I'm going to pull this out. And we will try it in our last substance. And it sinks down to the bottom. So much like the low density polyethylene, we know it's somewhere between the 0.9 and the 0.94. We don't know exactly where, but it's somewhere between those. Finally, we're going to try a piece of the polystyrene. Now, we're not going to try the foam. The foam would float, but it's got air in it. So that doesn't really tell us about the polymer. It tells us about a foam made with the polymer. But if I take just this piece of plastic and I stick it in the water, make sure there's no bubbles, and it drifts right down to the bottom. You might not be able to see it, but it's sitting right on top of that black triangle. Okay, so that tells us that the number 6 is more dense than water, has a density greater than 1. So this is one way we can determine what kind of plastic we are looking at. All right, so we've looked at some plastics that are recyclable, but some things don't have that triangle of comparison. And oh, I forgot one more I'm going to put here. Okay, so I have a spoon that is labeled as compostable. So most of the time when you see compostable plastics, they are made out of polylactic acid. So this is a plant-based polymer rather than coming from fossil fuels. And then we have a balloon that is made out of latex. And we have a rubber band made out of rubber. So latex and rubber are natural polymers. And then Teflon is a man-made polymer. So you're probably familiar with this from the coating of pans to make them non-stick, but we use it in chemistry to make this tape, and I'll show you that better once I pull it out of there. And then I have a plastic toothpick and a piece of ribbon, and we don't really know what those are. They weren't labeled. So let's take a look at some of the properties on these. So for our spoon, we can tell it's keeping its shape pretty well. It's not too flexible. In fact, if I try to bend it too much, it snaps. But if I pull on it, this is my tensile strength. Pulling on it doesn't really stretch it out. So it's pretty strong tensile wise. And it's not elastic. Now, if I look at latex, this is something that I can stretch out and it comes back. So it is elastic. This one's opaque, obviously. And it's very flexible. It's changing its shape quite a bit. Similar to the rubber band. This one, I can move it all around into different shapes, right? And I can stretch it out and it comes back to its own strength, size. So it is elastic there. My toothpick is going to be a lot like the PLA here, the spoon, where it's a little bit flexible, but if I try to bend it too much, it'll snap. That one's doing a lot better. So it's actually deforming. There it goes. It snaps, right? Um, Pretty strong if I pull on it. So good tensile strength. My ribbon here has pretty good tensile strength, and I can make it pretty flexible there, wrap it around. So we have that. You can tell that most of these are opaque. They're not see-through. All right, now I'm going to put my phone down as a background here. So this is the Teflon tape. It's actually white. And unlike most tapes, it's not really sticky on one side. It sticks together with static electricity, but it has this really unusual property. So you can see it's kind of like a rectangle that you would get off of a roll of tape. There you go. Okay, now it's opaque, obviously, and if I try and pull it in this direction, not much is happening. So good tensile strength in that direction. But if I turn it this way and pull on it, I get that necking going on. And so this is happening because all of the fibers are lined up along the length of the tape. So when I pull in this direction, there really isn't any further they can go. But when I pull sideways, they can separate from one another. So we get that strange stretching in that direction. All right, so those are our different types of polymers. I suppose I'm supposed to show you the abrasion. So if I try and scratch these with my finger, I get a little bit of a mark on the rubber band. The others, they're pretty resistant to abrasion. Not much is going on when I scratch those. All right, so school glue has in it a polymer called polyvinyl acetate, and that's very similar to another polymer called polyvinyl alcohol. And these are polymers that are like long spaghetti strands that if you think of spaghetti cooking in a big pot of water, they can slip by one another. But if we take that polymer and we join each spaghetti strand to one another, then they're not going to slip by each other very well. So this is a cross linker. It's made of a 4% solution of borax, which is a laundry booster. And so what we're going to do is we're just going to add this in here. I'm going to add about half of it, and then I'm going to try and stir it up. So you can see initially I can stir the glue pretty well. And now, instead of coming up as a liquid, it's sort of forming as a blob. And so as we mix in more of that borax, the less it is like a liquid and the more it's like a piece of putty. And so those strands can't slip by one another like liquid anymore. And this is the effect of a crosslinker. And then once it's in its putty form, you can move it around and play with it. As long as you've added enough borax, then it will not be too sticky. And that's one way that you can make a slime or a putty depending on how much borax you've added. And there's some that hasn't gotten borax on it. Okay, we have a couple of specialized experiments that we want to do. So one of them is to see whether or not these things are thermoplastic. Now, anything that is recyclable should be thermoplastic. That means that you should be able to um, heat it up and have it melt into some sort of liquid form that you could reshape. But we're going to, in particular, test the number 6 because this is the kind of plastic that they use to make shrinky dinks. So I have a piece of number 6 plastic here, and I'm going to put it over the top of this film here. And I'm just going to color over the top of it so that you can tell that oops, I got a hole in there. That it's the same size here. I'm just using a Sharpie here. Sometimes you'll see these where they've got it a little bit frosted, so that's got some abrasion to it, and you can color it with colored pencils. But most of the time, if you find these on like the lids of cookie containers or other food containers, then you have something that is clear. Okay, so we can see that this is the same size as the original. And so I will go and stick this in an oven, about 350, 320, 300, and we're going to let it sit in there just a minute or two, and we'll see what happens. Okay, so here you can see our plastic has shrunk quite a bit. It's curled up a little bit. They do tend to do that. And here's the hole that I mentioned before that I didn't want to write over the top of. So that hole is still present in there. So the number six plastic, we've shown that we can change its size by heating it up. So it is definitely thermoplastic. Okay, for our next experiment, what we're going to do is we're going to take some water. So this is just water in here and some sodium polyacrylate. Should write that upside down. But anyway, and so if I show you inside here, it's a powder. It's only barely covering the bottom of this, and we're just going to pour it in the water, see what happens. Get it underneath the water. So it got dark at first because it was absorbing it all. And you might be able to tell it looks like it's starting to grow now. So sodium polyacrylate is what they sometimes call diaper polymer. They put this in diapers because it will absorb a lot of the pee from the baby. Okay, we're going to test the chemical reactivity of some of our plastics. So in here, I've got a liquid acetone. So I have a styrofoam polystyrene peanut. And so I'm going to stick it down in here. And it's bubbling and foaming a little bit, and you can see it's disappearing. So it dissolves pretty readily in there. So we know that the polystyrene will dissolve in there. We can kind of test this with some of our other materials as well and see if they will dissolve. So I'm going to take some of my bits of plastic that had the numbers on them before and stick them in there and see what happens. So remember that my my black triangle was a number 1, so I'm going to stick that in there. And I'm going to take my number 4 and my number 5, and we'll stick these in here, see what happens. Turn that over so we can see the number. And let's see, what else did we have? The 6 dissolved, we've got 1, and then we need a number 2. So this one doesn't have a 2 on it, but it says HDPE, so I know that this is also number 2. And so I'm going to stick that in there. And so at least with reference to acetone, these seem pretty stable. I'm not seeing too much going on. Now we do know that some plastics hold up better to oils and things. So for example, number 5, the polypropylene is really good at being resistant to oils. And so a lot of times your margarine containers or your sour cream might be held in that. I'm also going to try this plastic lid, which is pretty clear right now. We'll see what happens when we stick this in here. This was also a number 1. And so it didn't dissolve, but you might be able to tell if I have a darker background that there's some frosting here. So it's becoming more opaque. So it's slightly reactive to the acetone.